Good day. I am Nomer Nidoy and this is my partner Maria Frances Bernice Dueñas. We are 4th year chemical engineering students and today we are excited to show to you our study regarding the PLA nanoclay glycerol nanocomposites for 3D printed wrist splints. This study was conducted under the guidance of our esteemed advisors, Dr. Persia Ada Indeiro and Dr. Ruth R. Aquino.
Through this research, we aim to develop a more flexible, durable, and sustainable alternative for wrist splints, improving both comfort and performance for individuals suffering from carpal tunnel syndrome. Carpal tunnel syndrome, or CTS, is one of the most common nerve disorders worldwide, affecting millions of people. It occurs when the median nerve in the wrist is compressed, leading to symptoms such as pain, numbness, and weakness in the hand. CTS is often caused by repetitive wrist movements, medical conditions like diabetes, or even pregnancy. If left untreated, it can result to severe muscle weakness and loss of hand function, affecting daily activities such as writing, typing, or even gripping objects. One of the most common treatments for CTS is wrist splinting. These splints are designed to keep the wrist in a neutral position, reducing pressure on the median nerve and alleviating symptoms. However, conventional splints have several drawbacks. Many users report discomfort due to poor fit, excessive stiffness, and lack of ventilation. Some materials cause skin irritation, while others degrade quickly, requiring frequent replacements. Given these challenges, there is a clear need for improved materials that offer both durability and comfort. To address these challenges, we explored the use of polylactic acid or PLA, organo-modified Montmorillonite or OMMT nanoclay, and glycerol to develop a 3D printed wrist splint with enhanced properties. PLA is a biodegradable, renewable polymer known for its strength, but it can be brittle. OMMT nanoclay improves mechanical reinforcement and thermal stability, while glycerol acts as a plasticizer, increasing flexibility and user comfort. By combining these three components, we aim to create a stronger, more durable, and comfortable wrist splint that is also environmentally sustainable. Before diving into our research, it's important to understand the baseline properties of PLA or polylactic acid, which serves as the main polymer in our study. PLA is widely used in biomedical and 3D printing applications due to its biodegradability and good mechanical properties. As shown in the table, pure PLA has a tensile strength of 35.6 megapascal, a tensile modulus of 3,420 megapascal, and a flexural strength of 85.2 megapascal, indicating its rigidity and strength. Its glass transition and melting temperatures range from 50 to 180 degrees Celsius, making it suitable for thermal processing. To put PLA into perspective, we compared it with other common polymers. While PLA has a higher tensile modulus than PVC and PP, it has relatively lower elongation at break, meaning it is more brittle. Compared to nylon, which has a flexural strength of 95 megapascal, PLA is stiffer but less flexible. These characteristics highlight the need for modification to improve PLA's flexibility while maintaining strength, which is the focus of our study. Now that we understand the need for better orthotic materials, let's go over our research objectives. The primary goal of this study was to develop and characterize a 3D printed wrist splint using a PLA OMMT glycerol composite. Specifically, we aimed to synthesize PLA OMMT glycerol filaments through melt intercalation, 3D print wrist splint samples, and conduct mechanical and thermal characterization, analyze the effects of OMMT and glycerol on strength, flexibility, and durability, and compare the optimized formulation to existing materials used for wrist splints. By achieving these objectives, we hope to enhance the functionality and usability of orthotic devices for CTS patients. However, PLA alone is brittle and hydrophobic, limiting comfort and durability in orthotic devices. Additionally, No study has explored the combined effects of OMMT and glycerol in PLA composites for medical applications. This study fills that gap by developing a stronger, more flexible, and comfortable wrist splint using a PLA OMMT glycerol composite. So why is this important? For PWDs, better orthotic support, comfort, and durability. For industry, enhanced PLA composites for 3D printing. For material science, new insights for future innovations. By bridging this gap, our study has the potential to improve both material science and healthcare applications. To develop and evaluate our composite material, we follow the structured experimental process. Material procurement, sourcing PLA, OMMT nanoclay, and glycerol. Composite synthesis, melt intercalation using a twin screw extruder. Filament preparation, pelletizing, drying, and extruding filaments. Sample design and fabrication, using on-shape and FDM 3D printing. Material characterization, testing mechanical, thermal, and surface properties. Data analysis, statistical evaluation via two-way ANOVA and HSD. 3D printing of CTS splint, fabrication of the final optimized wrist splint. Each step ensures that our material is suitable for orthotic applications, balancing strength, flexibility, and durability. We first evaluated the tensile properties of our PLA OMMT glycerol composites. The tensile strength results showed that 0.5 weight% OMMT and 3 weight% glycerol had the highest value at 33.57 megapascal, while 0.5 weight% OMMT and 5 weight% glycerol had the lowest at 22.73 megapascal. The addition of glycerol increased flexibility but slightly reduced tensile strength. In terms of tensile modulus, 0.5 weight% OMMT and 3 weight% glycerol also exhibited the highest stiffness at 1746.06 megapascal. These results suggest that while glycerol enhanced flexibility, higher OMMT concentrations improve stiffness. For flexural properties, 1 weight% OMMT and 3 weight% glycerol exhibited the highest flexural strength at 58.48 megapascals, demonstrating excellent resistance to bending forces. However, its high modulus of 2411.14 megapascal suggests that it may be too rigid for comfort. Meanwhile, 1 weight% OMMT and 5 weight% glycerol achieved a balance between strength and flexibility with a flexural strength of 45.60 megapascal and a modulus of 1804.43 megapascals. These results highlight the importance of optimizing both OMMT and glycerol content to achieve a comfortable yet durable material for wrist splints.
Considering both tensile and flexural properties, the 1% nanoclay and 5% glycerol was identified as the best formulation. While the 1% nanoclay and 3% glycerol had higher mechanical strength, its increased stiffness could lead to discomfort. On the other hand, the 0.5% nanoclay in formulations had lower strength, which may compromise durability. The 1% nanoclay and 5% glycerol provided the optimal balance of strength and flexibility, making it ideal for wrist splint applications. To further assess the suitability of our composite, we compared its flexural properties with those of conventional wrist splint materials. Our formulation exhibited higher flexural strength than virgin PLA and nylon, ensuring better load-bearing capacity. While PLA composites with calcium carbonate had higher stiffness, their rigidity could cause discomfort. Our material's balance of strength and flexibility makes it a promising alternative to conventional splinting materials. We conducted a two-way ANOVA to assess the significance of the nanoclay and glycerol concentrations on the mechanical properties. The results showed significant differences across formulations. This confirms that both additives influence a material's performance. The HSD test further identified which formulations differed significantly. This reinforces our selection of the 1% nanoclay and 5% glycerol as the best candidate. Thermal analysis was conducted to evaluate the stability of our material. DSC results show the glass transition temperature of 60 degrees Celsius and a melting temperature of 161 degrees Celsius, indicating improved heat resistance compared to that of virgin PLA. TGA revealed a degradation range of 300 to 400 degrees Celsius, confirming high thermal stability. These results suggest that the addition of the nanoclay enhances the thermal performance of our composite, making it more suitable for long-term use. To examine the fracture behavior, we conducted optical microscopy on a tensile sample of the best formulation. The images show that glycerol improved flexibility, reducing sudden failure, while nanoclay dispersion influenced the fracture behavior. Sample 1 had rougher fracture surfaces, suggesting better energy absorption, whereas sample 2 had more brittle characteristics. This confirms that our formulation enhances toughness and impact resistance, crucial for orthotic applications. We also evaluated the wettability of our material through contact angle analysis. Our formulation exhibited an average contact angle of 57.25 degrees, significantly lower than that of virgin PLAs, which is 74 degrees. This shift towards hydrophilicity is due to the presence of glycerol and nanoclay, which improves the surface interactions. Enhanced wettability is beneficial for biomedical applications, as it improves adhesion and comfort. FTIR analysis confirmed the successful incorporation of nanoclay and glycerol into the PLA matrix. Key peaks corresponding to the PLA, glycerol, and nanoclay were identified, verifying their interactions. Interestingly so, the FTIR software matched our composite spectrum with cellulose propionate, a material known for flexibility and durability, and is also a thermoplastic commonly used in the biomedical field. This similarity further supports the potential of our material for wrist-splint applications. Displayed on the screen is our final 3D printed wrist splint, which was designed specifically for carpal tunnel syndrome to provide both structural support and comfort. The design was sourced from Thingiverse, selected for its ergonomic fit and neutral wrist positioning, which is crucial in reducing strain and inflammation. To enhance its mechanical performance, we optimized the printing settings using Super Slicer. A rectilinear pinfill pattern was applied to the top and bottom layers to ensure a smooth and durable surface, while the middle section used a 25% gyroid infill pattern. This choice improved the flexibility and comfort without compromising its structural integrity. As for the printing process, we used an Ender 5 Plus 3D printer with a nozzle temperature of 190 degrees and a bed temperature of 60 degrees Celsius. These parameters ensured proper layer adhesion, minimizing warping and defects. The combination of our material formulation and optimized print settings resulted in a wrist splint that is lightweight, flexible, and durable, ideal for long-term CTS management. To conclude, this study successfully developed PLA nanoclay glycerol nanocomposites for 3D printed wrist splints, optimizing comfort, flexibility, and durability. The 1% nanoclay and 5% glycerol formulation exhibited the best balance of mechanical strength and flexibility, making it the most suitable candidate. Thermal stability, improved hydrophilicity, and effective dispersion of nanoclay and glycerol further validated its potential for biomedical applications. To enhance its performance, we recommend additional mechanical testing for long-term durability, wearability and biocompatibility assessments for real-world use, optimized processing techniques for better nanoclay dispersion, and exploring additional additives for improved functionality. This study lays the groundwork for customizable, sustainable, and high-performance orthotic devices for carpal tunnel syndrome treatment. Moreover, it extends beyond the improvement of wrist splints. It redefines the approach to designing biomedical materials with enhanced comfort, durability, and sustainability. Through the development of the PLA nanoclay glycerol nanocomposites, this research takes a significant step toward bridging the gap between material innovation and real-world applications. The findings pave the way for a future where wrist splints are not only customizable and durable, but also eco-friendly, contributing to advancements in both patient care and sustainable manufacturing.